So my talk will have a bit of a different character as the last talk. I think it will be a little bit more philosophical. It's also kind of my job. I'm CTO of a company, so what does that mean? That's always an interesting question. And what I found out what it means is that you zoom out and you zoom in, you zoom out and you zoom in. That means you zoom out, get an overview of what's going on, and then zoom in and work on some problem. And for me, that means I code sometimes, and otherwise I'm busy with strategic stuff. So zoom in, zoom out. And I have a bunch of processes going around in my head, and instead of telling you, giving you a whole lot of interesting information, I'm gonna do a mix of the kinds of questions I'm struggling with, and I'll end with a question. So this is me. I'm the co-founder of a company called StackState. I'm the CTO. I love programming. I love math. I'm a big geek basically. So what am I going to talk about? I'm going to talk about root cause analysis, and specifically I want to talk about temporal root cause analysis. Let's frame that a little bit. I'm talking about root cause analysis in terms of incident response. So if something goes wrong, you want to find out what the root cause is so that you can fix it. And StackState is a company that creates a product called StackState, and that product helps you do root cause analysis. It has an automated root cause analysis feature. And as they say in software, it's never finished. This is also never finished, and you can always go deeper with root cause analysis. So this is the big bang, and that's where the problem starts. So if you go back to the root cause of all problems, then it starts with the Big Bang. And so that's a bit problematic. So we have to find some decent ways to talk about root cause analysis. And I'll show you how we do it right now, and then start talking about the ways that we are moving forward with that. So first of all, we need a model. So in order to do root cause analysis, you need to have some understanding of what's going on. And you build a model, and so the model has to be of the right type of data. So here we have the Earth, so that might be interesting for maybe finding out how the tectonic plates move. I mean, then if I look at this picture, it might be just enough information to figure that out, but maybe not. You have to look at which data you want to collect and in what kind of model you're going to put that. So we invented a model which we call the 3T model, and that is about telemetry, topology, and time. So this is the heart of our software, and it builds a model of your entire IT operations in production, in acceptance, in tests, in the different data centers. It creates a full stack picture of everything that's going on. And for that we need something abstract enough to be able to capture everything, but concrete enough to be useful, which is always very difficult actually. Let me show you what our 3T model means. So I have I made a YouTube movie a little while ago. So this is a graph. So the word graph, when I talk about it, means a network. And also sometimes I use the word topology as well. So a graph is just some components that have some arrows pointing at each other. That means that I have a system that has some components, and those components depend on each other. And that's abstract enough to be able to model even, for example, a human body. My brain needs glucose to function. Glucose needs to go through the bloodstream, so my brain depends on the bloodstream, which depends on my heart pumping, but the glucose has to come from my blah blah blah, blah, blah like that. So here we have a topology. And I'll go a little bit into that, what that means. I'll skip through it. Here I made it a little bit more concrete, so we have some, some Docker image depending on some Docker container, depending on some database, depending on some Java application, blah blah blah. It's just a random model. And when something goes wrong, you can see here there's a component that went to red. Now these two components that depended on it also went to red. And that's useful. Even already that is very useful, because what you typically find in organizations is most of the time when there's an incident, when some failure happens, most of the time is still spent on finding what the problem is. The last report that I read said something like 60% of the time is still spent on finding what the problem is. Well, that should be actually the simplest thing. It's actually turns out to still be the hardest thing. So even if you have this model, it helps a lot, because then, for example, when the website is down, which is a very high level problem, you can very easily find, okay, that was caused by this application, but it might be a few steps removed. Now you can see there are two problems here in this model, and this is also very typical. Now, if you look at this model, it's very easy to see where the two problems are originating from, and it's also easy to see what kind of impact that is causing. That's very important as well, because sometimes it's very hard to distinguish impact from root cause. And another thing that happens a lot is if one thing goes down, that causes another thing to go down or to misbehave, and then you get something that's called an alert storm. So, what is important though in this model, I'll let it run now, is that you have this topology not only at this moment, but you have this topology running through time. So you can see here the time plane, and it's moving towards the future. It's important to get time, so I'll go into what I call temporal root cause analysis. Sounds very fancy, but just means we involve time. Here you can see some lines coming out of these components. So the lines represent telemetry. So for each component, you have some telemetry, which means metrics. You have event logs. You have traces. Everything that you might gather as kind of continuous flow of data. And so when you think about the heart, you can think about the heartbeat. So the component is always there, but the heartbeat is some kind of telemetry. So in this model, when something breaks, then
it doesn't want to break.
Then what is important is that you have the time before that. So here you can see the topology float up. So what happens actually is you have a topology, which is the current connectedness of your system with continuous delivery and with all the movements in automation and microservices and so on. This is going a lot. It's changing also very rapidly. So that before you just drew your topology on a Visio diagram, and then you were finished for about a year. And nowadays it's just changing all the time. So those changes are important, but it's also important that you know per component what telemetry is that you have for this component. And then when something breaks, you want to have the state before. So this is what's happening here. The state is still there where it was. So this is, in a glance, it's the 3D model that we have. And that's, I made this I made it abstract, the picture, because I want you to understand it in abstract terms. I'll go into it a little bit later. So we have the big five, which means the different ways of getting topology in place, so dependency mapping. So you can do it manually, you can do it with discovery, which means you just have some software installed and that will look for what's going on. You can have service registries, routers. You can ask your router like which components do you know are in your IP table, but you can also have, for example, which is a very popular, for example, you have a console or a zookeeper that knows how to connect components to each other. So the components, they register themselves, and when they want to talk to another component, they ask the registry. And so those registries are a way of getting the topology. You have trace information, which is, a request comes in and that drips down through your system, and from that you get a trace. And then we get to the automation and deployment tooling part. So if the kind of solution that we are building would not have been possible 10 years ago, because the last bit was not prevalent enough. But nowadays we see everywhere that everything is being automated. We have continuous delivery, thank God. So we can use the information that trickles down right from the beginning till the end. We can use that information to build this kind of model. And this is where I want to involve you guys, because to think about the connectedness of data. That is not something that happens a lot. We find that I go to a company and I ask them, okay, so what kind of topological information do you have? They say, oh, we don't have anything. I hear this a lot. And then we ask a little bit, are you maybe using some automation tooling somewhere, or do you maybe have a registry somewhere in your network? Are you using routers and blah, blah, blah. And then it turns out that they do have that information, but they never really thought about it. And since this model is kind of the base for what we chose to build our solution on, for us it's very important to have the connectedness for in our model, this topology. And it turns out that a lot of people don't think about how can we make sure that stuff is relatable to stuff, which is and with automation it becomes a lot easier out of the box, but it still requires you to think about it. And so this is kind of where I'm heading with this talk. So I already showed you this, but this is kind of a screenshot of our solution. Here you see what you could call spatial root cause analysis. So you can see that there's a system there at the top, your credit service, and that has a problem now, and that is related to an ESX server there at the bottom. And you can see also that there's some other impact happening. So this is already, as I said, it's very useful, because now if you have an alert storm, it's very easy to find where the problem lies. And also it also gives you the ability to monitor at the top level. So you might not be interested so much in, I have a database that is down, or maybe it's not so important because I have more stuff to do, and right now everything is still on a high level. My business is not at risk. So it gives you to know not only what the root cause is, but also what the impact is. It gives you the ability to prioritize, which is something that is important. So here I'm going to kind of leave the topology part for the spatial root cause analysis, but now we're going into the temporal root cause analysis. Yes.
Quick and stupid question. Why is web server 3 not connected to the hypervisor layer, or at least the services layer?
I have no idea. Just it could be anything. I don't know. In this case, it's just an example.
It's somewhere else.
There's reasons. I don't know.
I'm trying to figure out what's the difference between topology and ontology.
Mm-hmm.
Do you have a reason for this to call topology?
Yes, we have a reason, but it's so first of all, ontology is more vocabulary for how you describe things. It's not so much a description of things. So you have a description of things, and then you want to describe how you can describe that, which is an ontology. And so there's an ontology below this description. So this is a description of a piece of infrastructure. But in order to describe that, we also have to describe how you can describe that, which is the ontology. And so we have an ontology, but it's not visible right now.
So maybe
That's
this is ontology plus. So there is dimension, space dimension.
Well, yeah, I mean the ontology is also a graph, and it would be very cool to be able to visualize that as well. But and maybe even this is turtles all the way down, because an ontology also needs to be described, and so you have ontologies for ontologies, but never mind. But I think where something becomes a topology and not so much an ontology is where it becomes more of a this is how it is versus this is how we will describe it, which is roughly speaking, I would say. So, when you read an incident report, for example, a post-mortem, there's always a description of what happened. And it's typically like, oh, there was a traffic spike, and that traffic spike led to some queue to fill up, and then that queue filled up, and that caused the out of memory, and that out of memory was detected by Linux, and that did a restart, and that failed, and therefore the whole thing was restarted, and blah blah blah. And it's like it goes from here to here to here to here to here to here. So would it not be awesome to get that report the moment you need it? So this is kind of in the business that I am in. What information do we need to be able to compile such a report in an automated way? So imagine an operator getting being called out of bed at 3 o'clock in the morning, and he's not only told that this does not work, but he's told this does not work because somebody committed some code which was deployed an hour later, which then 5 hours later caused this thing to go there, and blah 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 blah. That would be cool. So in order to to be able to automate that, you need some kind of time travel. So we're also working on our graph is not only a graph in the current time, but there's also a graph that every change that happens in that graph you have to remember. And that's part of our ontology. So time is part of the ontology in order to be able to create an automated report like that. Here's a simple overview of an alert storm. In this sense, it's also easy to see that maybe the problem starts there. So if you look at it spatially and if you look at it temporally, you might actually see different causes. But both of them are very interesting to know. But of course, if I say the problem starts there, that is the question, because of course it doesn't start there. It maybe starts at birth, or it starts even earlier. One way to step back is to look at the continuous delivery pipeline. So if we want to have some kind of temporal root cause analysis, maybe we want to see all the state changes in the pipeline, and maybe there's multiple of these pipelines feeding into production. And so this is where it becomes, for me, I'm not quite sure yet how, but this is something that we're working on. In StackState, we have a model that shows you exactly how stuff is connected. It shows you also what is changing. So we can show you like these are the changes that happened that might have been related to the failure that we see, but we want to go back even further in the pipeline, and this is where it becomes a bit more. I'm not sure yet. So this is the where I take you with me in my thoughts. But you know, I'm a bit of a math geek at the same time, so I kind of tend to think in these kinds of things. So about, you know, inflection points and so on. Here's this reminds me of conic sections as well. I don't know if you know about, but if you have maybe it's not that interesting to know, you know, where stuff starts, because it's only interesting to know the critical moments. So what am I talking about? I'm talking about, like, for example, there was a software engineer and he was writing a piece of code, and then his manager came to his desk and interrupted him while he was writing something really difficult, and he had it perfectly in his mind, but this manager said, like, hey, when is it finished? And then he messed up, and you know, somehow that went to production, and that caused the problem. So there was this critical moment that, you know, it could have been prevented there. I see a lot of incident reports, and I find that almost all incidents that happen are what I would call a clusterfuck, because if it's one thing, then it usually doesn't get to production, because we're clever enough to get rid of these problems that are caused by one simple thing. But it's typically, you know, they're typically a couple of these moments. So this was maybe the first moment, but then there was still a code review, and then why did the code reviewer not find it? And then maybe there was a QA engineer that found the issue, reported it, and somehow it still went to production. And so it's about finding those critical moments, because we have a time traveling graph database, so we have to actually kind of find the most likely changes that led to the failure. And so where do you stop?